Alright, hell yeah. So we have dynamics, this is part 8, and we're doing differentiation. And I guess what I did not go over was actually how to set up the problem, because trigonometry is maybe the hardest thing to see. So we're going to look at this. This is a disk that spins around this point. So it's kind of like oblong. So when the disk is down here in its lowest point, this actuator, like the disk, will look like a circle like this. So this follower will be all the way down here. And then when this disk is in its highest point, it'll be like right up there. This follower will be right up there. Okay, so this problem states that this thing is spinning at a constant speed. So here's the angle that it's playing out, and this angle per unit time is that constant number. That's going to be the angular acceleration. And in radians per second, this term is going to be omega. So we have omega is the change in this angle, change in time, and that's going to be radians per second. So the angle is in radians, and the time is in seconds. All right, so what they want to know from the differential equation part is the velocity of this follower. And so I'm kind of new to this, diving deep into differentiation, but it's kind of cool how you get to start off with just the geometry, just the shape of something, and maybe like take a photo of it, like as a snapshot in time. So in this problem, they're just saying, hey, at some angle theta, the thing is out here, and this is where that follower is. So you could imagine when this is at the top, the angle is 0. So I'm gonna just assume that that's kind of where we're starting. Okay, so yeah, even I get kind of a little bit confused, but we are going to play out, kind of this angle. So just right at this snapshot in time, you can say this snapshot's like the angle of 30 degrees. You could say the time, if we do that, we could easily figure out the time of 30 degrees because we know how many times it's going to revolve in a minute. This is going to be 17 times a second. That's going to be 6,000 degrees per second. So every second this thing's going 6,000 degrees. If I just want to go 1 degree, that would be 1/6000th of a second. If I wanted to go 10 degrees, that would be 1/600th of a second. So that's kind of to get you in the ballpark. 1/600th. I don't even know what the hell that is. But we would have 3/600ths. So we would have 3/200. We would have 1/200ths. I don't know what 1/200ths is, but I do know what a hundredth is. That's going to be 0.01, and hell yeah. So this time frame is going to be 0.02 seconds. So kind of cool ways to kind of hone in on what's happening without having to break out your calculator. All right, so this is that snapshot in time. And so how do we set up what are we looking for? That's kind of the number one question. We want this height. Even though we want the velocity of this thing and the acceleration, just know that, hey, we just maybe want its position, because that's kind of the echelon of, I always do like jumping off a cliff into some water, and if you're over here jumping off the cliff, cool, your velocity is 0. We know acceleration is, 10 meters per second squared. And so maybe in a second, because this is our acceleration, maybe 1 second later our velocity is 10. Cool. What's our position? Well, we have an average velocity of 5, so our position is 5 meters, and so forth. Why did I even do that? Oh yeah, hell yeah. All right, so we just calculated that, our little guy is at 5 meters. So if we can figure out how we calculated this guy at 5 meters, maybe we can calculate in the next second where this person's going to be, in the next second. But anyway, so let's go back to this. If we can find this height of this follower based on the inputs that we have, cool. Then we can take that differential equation. We can change, the change in this height is velocity. So that's kind of how we get velocity. So from the geometry point of view, that's kind of what we're shooting for. So I'm going to call this like y, and we want to know that height in terms of something that is changing, you know what I mean? So in terms of this angle, but we're just going to take the angle at any kind of snapshot. Okay, so since we have that, now we're going to kind of fill in the geometry. This is the eccentricity. It's where this pivot is compared to the center of this disc, and so that doesn't change. So we're going to put E right there. This is 60 millimeters. So now the radius. Anytime you get a circle, hell yeah, you can put a radius in here. I can put a radius to there. I can put a radius to there like the picture. I can put a radius anywhere. And guess what? I can put a radius up to A. So that's kind of the next step in the process. Hell yeah. So now we know this is R. Cool. And so we have a big triangle, and it's not a right triangle. So if you got a big triangle that's not a right triangle, you know, trigonometry says, hey, let's make it a right triangle. All right, booyah. So now we have, well, two right triangles. You know, 90 degrees there, 90 degrees there. Hey, we already know something about this triangle. Now since we're getting into the geometry, the most important thing to know is that if you do have a right triangle, all you need to know is two things about it. If you know two things about that right triangle, you know everything about that triangle. So in this case, we already know one thing. We know the angle. You know what I mean? We kind of played out that angle. Oh, and then guess what? Booyah. We know this eccentricity is 60 millimeters, and this is unchanging. We know that this radius is unchanging, but okay, let's just focus on this triangle. We know everything about this triangle, so then we can kind of start labeling it. Now, do we know anything about this triangle? Well, we know the radius, but just as is, like, hey, I don't know this angle. I'm going to call this angle phi. I really don't know. You know, I mean, right now I just couldn't guess what that angle is. You know, so there you go. So I don't know the angle. I do know one thing, but that's it. I don't know this distance. I don't know that. Okay, sweet. But what we're going towards is that if you have two right triangles connected, well, maybe you don't need to know two things about this triangle. Well, yes, you do. You still need to know two things about this triangle, but from that perspective, hey, these two triangles have a side in common. So let's flip to this one. And now I know everything about this triangle. I know that side. So now let's flip to this one. Whoa, we have a right triangle, and guess what? I know two things about it. I know this side, and I know that. So now I know everything about this right triangle. So I think that is going to be kind of the aha moment, you know what I mean, of this video. And so we're going to kind of finish the geometry. If I have this angle, always draw the sun, you know, sun rays shining, and that's going to be over here on the sine component. You take the bigger number, the hypotenuse, because sine theta is a percentage between 0 and 100%, we're taking that larger number, the hypotenuse, and then multiplying it by a smaller percentage. That's going to give me that, okay? And if that's the sine component, this is going to be e cosine theta. Hell yeah. And so now what we do is we come, but okay, so now like let's take a step back. What the hell are we trying to do? We're trying to find this height in terms of something we know, like in terms of one variable that's kind of changing. If we could find this height in terms of E and R, you know what I mean, and that's all we need to know, hell yeah. And when the angle is 0, we're just going to have E plus R. But guess what? When this thing starts to spin, we just don't know this. This dimension changes. It's going to get less. It's not just E plus R. So with the differential equations, we're basically just trying to get this length for any theta. You know what I mean? So hey, we have this portion in terms of theta. We need to get this portion in terms of theta. That is ultimately what we're trying to do. We want to get y as a function of theta is just all this stuff theta plus all this stuff theta. Who cares, right? And then we're going to differentiate. We're going to take a dy of theta dt. The change in this length, you know, per unit time is going to be the velocity of that slider. Hell yeah. And then the equations in terms of theta. So when we take when we derive this d dt, hey, I don't see a t here. I see a theta. So that's where you have to use the chain rule. You have to go d theta, all that jazz theta, all that jazz theta. And then just make sure at the end you go d theta dt, which is angular velocity. It's the omega that you're going to put in, which is in the problem. All right, so that's kind of the, using geometry to kind of set up the problem. So we do need this height in terms of theta. So anytime that you're using geometry, breaking out your triangles, for the love of God, do not forget about Pythagorean's theorem. You know what I mean? It seems like such a, I don't know, just middle school equation. And it seems like I don't need to use it because don't we have these things called sines and cosines? And isn't that where we're going with, trigonometry? Nah, you still are, this is kind of, this is gold because you can use it in so many different ways. All right, hell yeah. And you can just break out identities. Sometimes you're just like, whoa, I amaze myself. It's just like, what are you saying? Are you saying this squared plus this squared is equal to e? Look what that says. That's saying e squared sine squared theta plus e squared cosine squared theta is equal to e squared. A squared plus b squared is equal to c squared. Hell, I can just factor out the e squared, and that gives me the sine squared theta cosine squared theta is equal to 1 identity. It's just like, oh no, I've never even thought to just even use Pythagorean's theorem right here. And I'm actually speaking for myself. I don't, So this is going to make your trigonometry skills so much better. Anytime you have a right triangle, analyze it from a Pythagorean's theorem point of view. And so right here, we don't know this angle. So instead of making a convoluted equation that relates this angle and that angle, what you could do, you could say that this is phi sine, this would be r, the larger number, the hypotenuse, sine phi. And then you could say these two equations are equal, and then figure out what phi is in terms of theta. But that's not the pro move. The pro move is to be like, whoa, we have Pythagorean's theorem, and but instead of having two sides squared and then taking the square root, which is equal to the hypotenuse, we already know the hypotenuse and we know one of the sides. So this is one you just have to kind of know from memory, and here's an easy way to know it from memory. We just take the hypotenuse squared. It's going to be the larger number. We must have to subtract it by this side squared. So that's e squared sine squared theta, and take the square root of it. Now that, hell yeah, is going to be this side. So let's write that in, and we're going to have r squared minus e squared sine squared theta. And all I did here was just take e sine theta and square it. And then because it's a product of two things, I can take the e squared and then the sine theta squared. And if you're not used to putting the squared on the sine theta right there, just know that that is equivalent to doing this. And do this for like a hell of a long time before you're just like, oh, I get that this is, I get that this is sine theta, sine theta. When I look at this, I'm looking at this mentally. All right, hell yeah. And so we take the square root of this, and so now we're ready to go. We know what y is. We know what this distance is. We know that y is equal to this plus this. So I guess we'll write it. We're good to go. Okay, hell yeah. And since we set up the differential equation, now we're in terms of theta. So if we do take dy dt, we have to use the chain rule. We have to take this entire thing with respect to theta, and then just make sure to do d theta dt. So this is your omega, this is theta dot. Hell yeah. Okay, so that was using the geometry to set up that differential equation, and then you can just go for it. All right, hell yeah. I think that's going to be a video, because in part 9, what we're really shooting for in both these questions, what I want to tackle is to, hey, we solved this equation in terms of theta. We got this height in terms of theta. Why couldn't we get it in terms of t? why couldn't we have something like sine squared, you know what I mean, something something t instead of the angle? You know what I mean? So we basically need to relate how is theta a function of time, you know, something something time. How is theta and time related? You know what I mean? Some sort of proportion. And hell yeah. And that kind of gets back to the kinematics that is using this equation, because in this problem, our angular speed is constant, but in this problem, they're saying, hey, this thing is going to start with a speed of 0 radians per second, and it's going to have constant acceleration. That is going to be equivalent of jumping off a cliff. Your velocity is 0, but you have constant acceleration. And so there is no constant speed in this one. You're going to be going from off a cliff 0 to hella until you hit, and the same thing here. That's why some of these problems get nonsensical after the time frame goes too long, because what is it going to do? Just speed up until it explodes? So, you know what I mean? So there is like, hey, maybe this is an electric motor. You're going to flip on the switch, and this thing's going to start up and get up to a constant speed. But right off the bat, you're going to have some acceleration, and maybe that's something you want to know. But for this problem, it's just constant acceleration. It's just a runaway wheel getting faster and faster and faster. And then they want to know how you get the equation. Now, the cool thing about that, so for part 9, is if you get this height, this distance y, as a function of t, then you can just differentiate with respect to t, and then you can just plug it into a computer. Go to derivativecalculator.com. It's an amazing resource. And then you can just put this in there as is. And you can take the first and second derivative. You can get the velocity, because deriving this distance y, you know what I mean, which is just the position A. You could say this is you know, the value, the magnitude of A. And it's a vector because it is just in this j hat direction. So you could say A of A j hat is, j, sorry, what the hell. Anyway, so you differentiate a position vector, you get a velocity vector. Differentiate that, you get the acceleration at A. And if it's just in terms, and because we're differentiating with respect to time, if we put this into a computer program, you need t here. Like I don't know, I haven't figured out like, well, could a computer program run the chain rule? So you could get kind of those theta dots and theta double dots, you know, as you differentiate with respect to theta, knowing that you have this also, you know what I mean? You need to differentiate this equation with respect to theta and then multiply by theta dot. And when you do the first derivative, hell yeah, this pops out. And then when you do the second derivative, you'll get a combination of two of these and then one of these per all your characters. But I just haven't figured out how to do that. So the way to do it on the computer is just, hey, if you're differentiating with respect to time, just make theta a function of time. And it's not that hard. It's the same thing as saying, hey, I have acceleration as 10. I want to know position as a function of time. You know what I mean? So that's going to be that 4.9 t squared plus maybe my velocity initial times t plus my position initial. You know, kind of the classic kinematic equation. Same thing with the angle. So kind of the foreshadow on, hey, I want to know this angle at any given time. Cool. You're gonna need the angular acceleration. 1/2 the angular acceleration times time squared. See how this was 4.9 is half of 9.8. And then plus the angular speed, omega times time. Very similar to velocity, plus where you started. You know what I mean? Maybe we started at 30 degrees. Cool. We're going to write that in. Theta naught is like 0.5 radians. You know, 0.52 radians, 30 degrees. All right, so hell yeah. So that kind of finishes this one. But yeah, I was just hesitant to do too many parts on this problem. But it seems like once I get the hang of it, the later parts are the more, you know. So we're basically going to finish up. And it might be two more, you know what I mean? Set this up as a function of time, and then set this problem up as a function of time. So this was part 8. Let's do part 9 and 10. We're going to first set this one up as a function of time because it has a double derivative. Well, no, it doesn't. This just has a single derivative, but still, you want to take that double derivative, and it gets crazy. Because they just get, you know, it's nice to have a computer, and so you might as well just get it as a function of time right off the bat, throw it in a computer program, and get those two derivatives, and then you're just good to go. All right, so hell yeah.